So we'll start now. So good afternoon, everyone. As a part of our weekly seminar, today we are happy to have Dr. Judit Szulagyi. Judit is an expert in planet and moon formation. So Judit completed her PhD in 2015 from Observatoire de la Côte d'Azur in Nice, France. In fact, me and Judit were batchmates and did a PhD at the same institute. So just after finishing her PhD, she joined ETH Zurich as an ETH fellow. Then she was a senior research associate at the University of Zurich. And in January 2021, she joined as an assistant professor in ETH Zurich. So Judit has received various awards. In 2017, she was chosen on the Forbes list of 30 under 30 in science for her contribution to the planet formation. And recently she received the Mirac Prize for Best Early Career Researcher 2021 in Theoretical Astrophysics by the European Astronomical Society. So welcome, Judit. And we thank you for accepting the invitation and agreeing to give an online seminar. So Judit, you may start your presentation now. You will have around 45 minutes for presentation and 15 minutes for Q&A. And I will ping you around 40 minutes later.
Okay, thank you very much. Thank you very much for this very nice introduction, and thank you very much for inviting me to talk to here today. So I'm going to talk about circumplanetary disks and their role in planet and moon formation. I first start with an introduction and introduce what circumplanetary disks are. So this is a simulation, a hydrodynamic simulation of planet formation. There is a planet which forms in this protoplanetary disk around the star. And as we zoom closer to this forming planet, we're going to see that there is a disk developing around the planet itself. This is the planet, and this is the circumplanetary disk that developed around the planet. And this is where the moon's going to grow later on. I schematized the moons with balls over here, but this is not part of the hydrodynamic simulation. This simulation was made with our Jupyter hydrodynamic code, and it not only calculates densities, but it's also solving for the temperature with radiative transfer. So the definition of the circumplanetary disk could be the following. It's a gaseous disk around the planet which formed within the planet formation process, as opposed to brown dwarf disks or circumstellar disks which form through the star formation process. And circumplanetary disks are really small disks within a large disk of the circumstellar disk. And actually, this circumplanetary disk is constantly fed from this large disk, from the circumstellar disk around the planet. Now we should distinguish this gaseous circumplanetary disk with circumplanetary debris disk, because sometimes circumplanetary debris disks do not form via the planet formation process, but they form as a result of planet-planet collision. So this is how our moon formed around Earth, that Earth was hit by a Mars-sized planet, and the ejecta formed a debris disk around our planet, which eventually formed the moon. But in that case, you know, the circumplanetary debris disk formed in a very different way than what I described previously. However, circumplanetary debris disk can also be an evolved stage of the gaseous circumplanetary disk, similarly as circumstellar disks evolve, that eventually the gas dissipates, and then you're left with the debris, the solid components, solid building blocks of planets. There are multiple importance for the circumplanetary material in general. Here is again planet and the circumplanetary disk inside the circumstellar disk. So first of all, they channel or determine how much mass can fall onto the accreting protoplanet. Therefore, it determines how big the planet can grow and what is the planet formation timescale. Now, these disks are the bird nest for satellites, or in other words, moons, to grow. So these circumplanetary disks also determine the satellite formation timescale and what types of moons we can form within these disks. And of course, the circumplanetary disk, through its composition, going to affect the composition of the planets and the composition of the moons that form within. And it's also surrounding the forming planet, which makes it obscured from our view. Therefore, when we want to do observations of forming planets, we really actually do observation of circumplanetary disks, since we cannot see down directly to the planet's surface. As you see, there is quite some material around. The atmosphere of the circumplanetary disk will also hide quite some of the brightness from the forming planet itself. So even for observational predictions, we have to take care about the circumplanetary disk influence on the observations. Now, I mentioned before that the circumplanetary disk is constantly fed by the circumstellar disk. And this is what I schematized over here in a 2D version. On the next slide, I'm going to show you a 3D movie about this circulation. Now, this circulation is happening because as the spiral wake of the planets are bringing up material inside the circumstellar disk, which then falling into the gap region and spiral down onto the circumplanetary disk and the planet itself. And the material which could not be straight away accreted to the planet, which is more than 90% of the gas that falls onto the circumplanetary disk, will be then spiraling outwards inside this circumplanetary disk and going back to the circumstellar disk and then rising up again to maintain this vertical, or how we called it, meridional circulation. So when we published this in 2014, 2 years later, a Berkeley group have found the same circulation in their simulation, so they confirmed the results. And then Dutch researchers also find the same exact circulation for terrestrial mass planets, so small mass planets as well. So regardless the planetary mass, this is how planet accretion occurs, that it's accreting vertically and there is an outflow in the midplane. What is really exciting is now this meridional circulation has been even observed with ALMA kinematic map information. And this was a paper by Richard Teague and colleagues in Nature in 2019. So now we know that it's not only happening in our hydrodynamic simulations, but it's also happening in real life. And this is how planets accrete from the vertical direction. So now I'm going to show you the movie with streamlines, gas streamlines. So here is the planet location, and I plotted some streamlines over here. With arrows, I showed the flow. It comes in the gap region, shock on the spiral wake of the planet, therefore losing angular momentum or losing velocity. It slows down, and therefore it can get accreted onto the circumplanetary disk. Now that's part of the gas which could not be straight away accreted, going to go back through the spiral wake back to the circumstellar disk. So this is a very complex 3D circulation, and this is why we need to have a 3D simulations for planet formation in order to really catch this whole complex flow. In the past, simulations were often constrained in the midplane, but then they would completely miss this vertical accretion flow. So this is why we now are using almost exclusively just 3D simulations. Now, what about the temperature? I mentioned before that our code can also calculate the temperature because it solves the radiative transfer with flux limited diffusion approximation. So this is the temperature map I am getting in the planet vicinity. Here is the planet, here is the circumplanetary disk. This is a very hot simulation. This is a 10 Jupiter mass planet at 5 AU from its star. And the color scale is logarithmic, is in Kelvins, and the peak of the scale is 16,000 Kelvin, which can be found deep within the planet. But you see that this forming planet surface is still a few thousand Kelvin hot. And then this temperature gradient is quite steep inside the circumplanetary disk. At the edge of the circumplanetary disk, we have a few hundred Kelvin. So the forming planet vicinity, not very surprisingly, quite hot because the accretion is quite much ongoing. There is also a lot of other heating mechanisms such as viscous heating and shock heating, what you see over here. So here you see this dark brown shock front on the surface of the circumplanetary disk, which created due to the incoming infalling accretion flow. And I show you here the actual streamlines from the simulations, which I color coded with the velocity magnitude. So the high velocities are green, low velocities are purple. We see that the flow is speeding up as it's reaching close to the planet, and then it hits the surface of the circumplanetary disk. Therefore, it's creating this shock front, which shows up with high temperatures. And then after the gas is passing through the shock front, we see that it's slowing down because the green goes to purple. So we can see exactly the angular momentum loss that happens by passing through the shock front. And this is why this gas could be accreted onto the planet's surface. However, on the right-hand side, we see another bunch of streamlines which did not slow down enough to reach the planet's surface. They still have too much angular momentum. They're going to go back onto the circumplanetary disk and eventually leave the planet vicinity. And this is why I mentioned before that more than 90% of the gas is not accreted to the planet right away. They're going to circulate around and going to eventually reach the planet, but not necessarily in one go. How I explain this to my students is that planets are not black holes. They don't have 100% accretion efficiency. They are very inefficient accretors, and this is the reason why we have relatively small accretion rate to the planet, and most of the gas is just passing through in the planet vicinity. So when we talk about this really high temperatures, few thousand Kelvin, even 10,000 Kelvin, then of course you can ask the question, what about ionization? Especially ionization of hydrogen would be very exciting, since hydrogen recombination lines could be detected from accreting objects. So I calculated with the Saha equation the ionization fractions in the planet vicinity, and now I really zoomed in close to the planet and the shock front of the circumplanetary disk. So if we go back to the previous plot, now I cut out this inner part. And this is why I plotted over here. And the ionization fraction is this surface with these green-blue colors. So wherever you see the surface there, hydrogen ionization happens. It can happen inside the planet, but then of course this will be absorbed by the surrounding material, and it can happen in the hottest part of the shock front on the circumplanetary disk, and this can potentially reach the observers. However, I find that this only happens if the planet is very massive, close to the brown dwarf regime, 10 Jupiter mass or more. Smaller mass planets will not going to create such strong shock fronts that could ionize hydrogen, and from the inner parts of the planet, ionized hydrogen will not reach the surface. So it's really difficult to detect forming planets with hydrogen recombination lines. So when we talk about circumplanetary disk, we can also talk about circumplanetary envelopes, because the circumplanetary disk forms after a circumplanetary envelope is forming. So if we think about how any mass of planet is forming, it's getting larger and larger. It's accrete gas, and the envelope getting larger and larger. The envelope's also cool. And when this protoplanet is massive enough and the surrounding is cool enough, then the circumplanetary envelope can collapse into a circumplanetary disk. And this is what opens the way for satellite formation. If we talk about small mass planets, then we only get circumplanetary envelopes, then circumplanetary disk never forms, and then we only get the first atmospheres or first gaseous envelopes of those planets. So it's really a 2D dependence or a multiple dimensional dependence, but there are more. These are the two things which really determine whether you form a circumplanetary envelope or a disk. That if you have a high mass planet, then more likely you form a disk around it eventually from the envelope. But also it depends on the surrounding opacity, or if you want to think about that way, the temperature. If the temperature is cool enough, then we can collapse into a disk. if the planet is too close to the star, then it's going to only form an envelope, and then it's never going to form satellite systems. So this is why it's also very important which planet can sustain a circumplanetary disk and which planet cannot. And then, of course, if we look into the solar system, this is the reason why we find the satellite systems in the outer planetary system, where the temperatures are colder and where we find more massive planets. Because these are the planets which form circumplanetary disk, and therefore these are the ones which could form moons around them. In the case of terrestrial planets, they cannot form circumplanetary disks, therefore they cannot form moons. However, of course, you immediately say, but hey, Earth has a moon and Mars has 2 small moons as well. There are multiple ways to obtain a moon, and that's not only the circumplanetary disk way. This could be planet-planet collision, as I explained before, for the moon of Earth. And it could be also a capture, which is hypothesized also for Phobos and Deimos of Mars, that they were actually captured asteroid belt objects. So there are multiple ways to have moons, but still the most robust way to form a moon is a circumplanetary disk. The other 2 scenarios are statistically less likely. And so in general, we can safely say that terrestrial planets not going to have moons, or very little chance to have a few moons maybe, but they're never going to have moon systems. So now, after this introduction, I would like to move on how we can detect forming planets and their circumplanetary disk. And for this, I released a paper series on the observability of forming planets and their circumplanetary disk. And the first regime I looked into was whether we can detect this circumplanetary disk with ALMA in submillimeter and radio wavelengths. So for this, I turned my hydrodynamic simulations, which also provided the temperature information, not only the density information, into an intensity image on a given wavelength with a post-processing radiative transfer tool, which is called RADMC3D and developed by Cornelis de Lemont, who is a professor in Germany. And then after that, I did the beam convolution, in this case with the CASA software, to incorporate interferometry, and this is how you get a mock observational image. So how your model going to look like or would look like in an observation. And here we see this ear, which is the circumplanetary disk within this gap. So this is exactly what we want to find. Now, I did this modeling, of course, on various ALMA wavelengths. So this is the shortest wavelength band 10 and 350 microns. And then we go towards longer wavelengths up to 2.1 millimeter. And the planet and the circumplanetary disk is always at 3 o'clock. And you see that we need to have large enough resolution in order to detect this point source inside the gap. But it's also clear that the shorter wavelength seems to be better to catch this hot circumplanetary disk, because again, it's hot, so you should go rather shorter wavelengths in order to catch this effect on the longer wavelengths. You're a little bit handicapped for both reasons, both the resolution reason and the temperature reason. So then after this, I determined, okay, it seems like 440 microns is the best, band 9 is the best to detect forming planets. And then I run it with various simulations where I put in various massive planets: Saturn mass, 1 Jupiter mass, 3 Jupiter mass, 5 Jupiter mass, and 10 Jupiter mass. And surprisingly, all cases could be easily detected with ALMA, even a Saturn mass case. So that was very good news, and we get ALMA time with that, and currently one of my students are working on to reduce that data. But some other colleagues were faster than us, and Isala and colleagues have published the first potential circumplanetary disk detections with ALMA continuum, so exactly how I predicted. In the PDS-70 system, this is PDS-70C. They also had a candidate around this other planet. However, now follow-up observations show that this is not a circumplanetary disk. So we have just this case, but it seems to be confirmed. So here we see, what we really see is the dust, the solids that are inside the circumplanetary disk around the forming planet. And then Christians and colleagues have found the circumplanetary disk with short, near infrared spectroscopy around the same planet component, so it's the C component. So we now have multi-wavelength information about the potential circumplanetary disk around this planet candidate. And these detections happened in the papers came out in 2019, May and June. So this is relatively recent. These were the first circumplanetary disk observations. Then as a second exercise after the ALMA wavelength, I went into the near-infrared, mid-infrared, so how this circumplanetary disk might be detected with NACO or ARIS type of instruments on the VLT. So we are talking about 2 to 5 microns, basically. So this is 2, this is KLM band. And different rows are the different planetary masses: Saturn, Jupiter, 5 Jupiter, 10 Jupiter. And here the planet would be at 9 o'clock. And as you see, it is hopeless for Jupiter mass planets or smaller. 5 Jupiter mass planets maybe, but take into account that I show you here a face-on disk, not an inclined disk. And also there is no noise added to these images. So I think even the 5 Jupiter mass case would be difficult. 10 Jupiter mass case, what is really could be detected in near infrared. So as opposed to ALMA, near infrared doesn't seem to be so good to detect these forming planets. I also compared the magnitudes that I got with planet evolution models. And of course, I found that the brightness what I detected was much lower than even the so-called cold start planet evolution models, which would predict the lowest magnitude possible. This is, of course, due to the extinction. That there is also extinction going on inside the circumplanetary disk material, so we do not see down to the planet. And unfortunately, I found that the brightness does not scale with the planetary mass. This is because because it depends on the circumplanetary disk characteristics. So what is the temperature, what is the density of the circumplanetary disk, which is affected by the circumstellar disk, which is feeding the circumplanetary disk. So this is the reason why we unfortunately cannot use brightness information to derive out or set a limit on the planet masses, because we do not see the planet, we see the circumplanetary disk, and the brightness will scale with that. And of course, extinction is a big problem, as I mentioned before. Imagine if this is the planet, the photons are escaping from here. It has to go through all this material, which is now the circumplanetary disk atmosphere. Even if you are face on, it has to pass through all this material. If we would have an inclined system, then it has to pass through much more material. And this is why it's so challenging to detect forming planets. In this paper, I also, for the very first time, derived out the spectral energy distributions of circumplanetary disks and compared it with circumstellar disk spectral energy distributions. What I did is making the contrast of the two SCDs in order to determine which wavelengths are the best to detect the circumplanetary disk on the background of the circumstellar disk. As you have seen the previous images, here we are not limited by the contrast in respect to the star, but really the contrast in respect to the circumplanetary disk, since the circumplanetary disk can be found within the circumstellar disk. And so we have to find that wavelength where we get the best contrast between these two disks. And this is what I found. I show you how exactly I did this. So I defined an aperture around the circumplanetary disk, took out the spectral energy distribution here. Then I took the same aperture in the opposite location, the anti-planet location, and derived out the circumstellar disk SCD and divided the two. And this is how I get this plot, which shows you that, say, 10 to 50 microns are really good contrast. So that's the best to detect the circumplanetary disk if the planet is a very massive planet, which opens a deep gap. But if you have a Jupiter mass or smaller, then it's not so good on that wavelength range. In those cases, the longer wavelength seems to be much better. And then again, we go back to what we found regarding ALMA, that it seems like submillimeter and radio wavelengths are the best to detect circumplanetary disk, not the near and mid infrared. And this is exactly the method that Christians et al. Used. So they had this near-infrared spectrum, and they found a near-infrared axis, which could only fit with a circumplanetary disk model. A planet-only model did not fit it, and this way they found this circumplanetary disk candidate in the PDS-70 system. Now, just yesterday, we get our third paper accepted. This is scattered light and polarization for instruments like SPHERE and GPI. So this is, again, near-infrared scattered light. And this is what we got. This is polarized intensity images for 10 Jupiter mass and then down to 1 Saturn mass. Again, only the 10 Jupiter mass case could be observed. Anything below is hopeless in terms of polarization, unfortunately. So I don't even spend too much time on that. I go on to the next one, which is hydrogen recombination lines, like H alpha, Paschen beta, bracket gamma. And this is a paper we did with Barbara Colano in 2020. She's a professor here in Germany. So why these hydrogen recombination lines? Because they are accretion tracer lines. That means that the line luminosity is scaling with the accretion rate of the object. And this is widely used all across astrophysics, right? And in the past, this relationship between the hydrogen recombination line luminosity versus the accretion rate was only determined for stars, not for planets. So people, even when they detected H alpha from planet candidates, which happened in 2 planet candidates like Cation 15b and PDS 70b, or some papers say it's C, but it's the same planet candidate. They used the theta formula to derive out the accretion rate, which I don't think is very fitting because, you know, planets are going to have a different relationship. And what we need to care about when we care about hydrogen recombination lines, of course, we have to ionize hydrogen. And that means that the temperature should be above 10,000 K or more. And of course, we are worried about line variability as well. So I use my simulations to derive out the hydrogen recombination line densities. Here is the temperature map in the planet vicinity and the ionization map that I showed you already before. And then I self-consistently calculated the line fluxes from the ionization rates with the photoionization code of Barbara Colano, which is called moccasin, and consistently calculated the extinction as well, which seemed to be the main problem for the detection. And we found that only 10 Jupiter mass planets or more can be detected with this hydrogen recombination lines. Lower mass planets cannot. And I think this is what explains why we have only 2 planet candidate detection in H alpha, because 10 Jupiter mass planets are very rare. And also we found some variability up to 58% of line variability, which is due to extinction, so the varied column density in this atmosphere region of the circumplanetary disk. And by the way, all the detectable flux was coming from the circumplanetary disk shock front, not from the planet. Of course, what is emitted from the planet will be absorbed by the circumplanetary disk material around. So for the summary of the observational predictions, it seems that in submillimeter and radio, we have the best chance. Even small mass planets like Saturn and below could be observed. With the other methods, only 10 Jupiter mass planets or more massive, so close to the brown dwarf regime. And this is why it is so challenging to observe forming planets. And I mentioned before that the take-home message is that unfortunately the observed brightness cannot be used to infer planetary masses because we detect the circumplanetary disk, not the planet, and therefore the brightness will depend on the circumplanetary disk characteristics, which depend on the circumstellar disk characteristics. And so the next thing what we did is looking into how dust influencing all these observational predictions and how it influences planet formation as well. So my former master thesis student, Fabian Winkert, who is now continuing with us for PhD, and he's co-supervised between me and Till Birnstiel in Munich. He developed a dust module into our Jupyter code in a multi-fluid approach. And we looked into how this now new dust and gas simulation look like in 3 dimensions. And we have 2 new papers that are on arXiv already, and we get the first and the second referee report for the 2. And here is the simulations that look like now. It's this whole circumstellar disk. The dust density is shown by orange colors, the gas density is blue colors, and we simulated here millimeter-sized dust. And it has all the feedback, or the coupling with the gas as well. And we were very surprised to find that the millimeter-sized dust is not confined anymore into the midplane. So if we would not put in a planet, of course, eventually, even if you put the millimeter-sized dust grains high up in the disk at T0 time, it will eventually settle down into the midplane. However, we find that when the planet's starting to grow, the spiral wicks are steering up the dust inside the circumstellar disk, and therefore the dust can be found far away from the midplane in the upper layers of the circumstellar disk as well, even the millimeter-sized dust. And this is very surprising. This is not what was known before. And exactly this spiral wick induced steering is due to this meridional circulation I showed you at the very beginning that we found for gas. These same mechanisms is steering up also even larger size grains, like millimeter-sized grains, pebbles, and then throw them up until the surface of the circumstellar disk as well. Here we showed vertical slices of dust density for the different simulations that we did. We studied different planetary masses, so 5 Jupiter mass, 1 Jupiter mass, Saturn and Neptune mass, which we put at 5 AU from its stars, 30 AU and 50 AU. What you see that the larger is the planetary mass, the more dust steering we are getting. So the further away the millimeter-sized dust is stirred up above the midplane, but also larger fraction of the circumstellar disk is stirred up in terms of this dust. If you have a Neptune mass planet, this dust steering can be found only very close to the planet. In the further away circumstellar disk, this effect is not visible. And this, of course, influences the local dust to gas ratio as well. So if we, for example, consider 1% dust to gas ratio, that layer above the midplane can be found further away from the midplane if the planet is higher mass than if it's lower mass. So again, this influences the local dust to gas ratio as well, which then going to influence things like streaming instability and so on. And then here I show you the actual streamlines for the dust velocities, and you see that the millimeter-sized dust is indeed delivered the same way to the circumplanetary disk region as the gas was before. I showed you the movie before, and here you see the very similar streamlines for the millimeter-sized dust as well. So this is very interesting because people before thought that, okay, the millimeter-sized dust or larger going to be held up at the planetary gap edges by the pressure bump, and they could not reach the circumplanetary disk. And therefore, people hypothesized that moon formation can happen if the circumplanetary disk somehow catches planetesimals from the circumstellar disk. Now, this is not needed because we don't have this pebble isolation mass anymore. That only happens in the midplane. But above the midplane, this meridional circulation very efficiently bridges over the gap region and can deliver even large solids like millimeter-sized solids into the circumplanetary disk, which then can grow further to eventually build moons or pebble accretion can happen, and this way building up planetesimals inside the circumplanetary disk. So the circumplanetary disk is not dust deprived, it's not solid deprived, because the meridional circulation constantly delivers solids also into the planet vicinity. And for the same effect, I show you the velocities for the dust, the Z component, so the vertical component. And I mentioned before that this whole circulation is driven by the spiral wake of the planet. And this is what you see over here. This is the planet location. And these are the spiral wakes of the planet that you see very well in this Z component. The red is upward motion. The blue is downward motion. The blue is where the planet is. And you see that indeed the spiral wakes are bringing up material and then down, up and down. But please mind that this is just one component of the velocity. So don't think that the flow is like that it's going up and down, up and down, up and down inside the circumstellar disk. This is just one velocity component. The real flow looks like this, what I showed you before. This is a three-dimensional vector, right? This is the streamline. This is how exactly the flow is happening. And this is what is really delivering material into the planet vicinity. Now, if we go back to the midplane and the dust densities, how our simulation look like, we find that one planet can open multiple dust caps, which is not our finding per se. There were many papers by other colleagues that have found the same. But if we now look at the ALMA mocks that we did from the simulations, we see that in these cases, we see multiple rings and gaps around the planet, even though there is just one planet, but we can have even multiple rings and multiple gaps observed because of this multiple gap opening. So what we found here that if planet is Saturn mass or more massive, the upper 9 panels, then we see these rings, gaps, and so on. If it's a Neptune mass or smaller, then we just see an asymmetrical ring, which is the spiral wake itself. The spiral wake in this case is going to act like a dust trap. And you see that it's asymmetric because at the planet location, it mismatches. And so it looks very different what kind of planet disk interaction we can see with ALMA if we have a Neptune mass planet or if we have a larger mass planet. And by the way, Fabian have derived the ALMA gap versus planet mass relationship. So if you are interested in something like that, you can look at it. We also took into account the beam sizes and various alpha various ALMA wavelengths. So it's very useful for observations to estimate planet masses. We also looked into what are the disk masses, since all this dust steering going to lead to that some of the dust going to be really hidden from our view. Of course, observations can see down to the optically thin to thick transition, so up until the optically thick part of the disk. So basically, here we show that the optically thick to thin transition, these are the lines at various wavelengths. So the observations can see what is above this line, but not below this line. That's the hidden mass. So what I asked Fabian to do to compare the hydrodynamic simulation dust masses, which are the real disk masses, with the one that he calculated from the ALMA mock observations that we did from the models, and compare the two. So this is like comparing the real disk masses with the observationally derived disk masses. And we found, of course, that ALMA observations are underestimating the disk masses by a factor of 2 to 10 times, partially because of this dust steering and this hidden dust that we cannot see in this observation. So this means that protoplanetary disk, planet-forming disk, can be 10 times more massive than what the ALMA observations are telling us, because unfortunately the ALMA observations and that formula can only account for optically thin part of the disk. So the take-home message is that if planets present in disk, then they can very efficiently stir up even the larger dust grains. And this is due to the meridional circulation, which is driven by the spiral wake of the planets. And that meridional circulation also bridges over the gap of the planet and successfully delivers solids onto the planet vicinity, which opens a way for moon formation. Pebble isolation mass is not a problem. And the disk masses from ALMA observations are underestimating the disk mass by 2 to 10 times. And with that, I just want to mention that I'm looking for a postdoc. We have an ETH fellowship program for which the submission deadline is September 1st. It is a very high salary. It is the highest salary in the world for a postdoc. It's over 8 million Indian rupees per year, if I calculated correctly, with yearly increments. Eligibility is that you have to have a PhD obtained 6 months to 2 years in comparison to this submission deadline, and have to have a matching portfolio to my research group. I'm also doing a black hole accretion disk simulation, so that's also possible. And even though it's not written in the eligibility criteria like this, but our experience is that the candidates have to have at least 5 papers to get this fellowship or more. So if you are interested and have a matching portfolio, then you can get my my contact details, for example, from Shubhendu. And with that, I thank you for your attention, and I'm happy to take questions, and I'm well within time.
Yeah, thanks, Judit, for such a wonderful presentation. Especially the simulations are really beautiful. So we now have time for question and answer. So please raise your hand or put your question in the chat box so that she can answer those. So any questions? Yeah, I see one hand. So Indranil, please go ahead.
Hello, this is a very good talk.
Thank you.
I was just wondering, what do you do to get those rings? I mean, how do you tell the code to do that? Because as far as I understand that if you have a protoplanet or something rotating through the disk, it is supposed to leave a wake, and that generally leads to these rings. So, but how do you tell the code to do that?
So I'm not telling the code to do that, right? We are solving for other relevant equations, the gravity, the hydrodynamics, the radiative transfer, and so on. So what happens, right, that planets open gaps in this disk. Due to the torques, it's going to push away the 2 sides of the disk. And because of that, at the edges of the gap, they're going to be an overdensity, and that's creating these ring structures, right? At the edges of the gap, they're going to be a pressure bump, which act as a dust trap, and there the dust going to accumulate. And this is why we're going to get these rings at the edges of the planetary gap.
No, that's the physics, I understand that. But what I'm trying to say is that for example, in black hole simulations, we don't see that, right? So what I was just wondering, there has to be some, physical information that has to go that will tell the code that, okay, once you have created the wake, so what I mean to say is if there's a disk, there's a fluid, and you are moving the protoplanet through that. So it's moving the matter along its path, but that the matter is not also coming back, right, and filling the gap once this protoplanet has moved away. So the physical condition has to be slightly different.
So it's a different regime, right? So here we care about the planet to star ratio versus a black hole to, say, black hole ratio would be very different, right? A binary case.
Sure.
And then of course, if you talk about dust, then That's also in the inner part of the black hole disk, it wouldn't exist because the temperature would be above silicate sublimation point. Here we are in a low temperature regime, but either way, I mean, even if there is still replenishment in the gap, they're going to be also clearing, and this whole torque thing is going to make the gap clear, and that's going to be always there, since the torques are just across the sum of the forces, and the forces are always are in effect. So small mass planets do not open gap, but if the planet to star ratio is high enough, then we get these gaps. And I think this is why we are talking about different secondary to primary mass ratios, and this is why the two cases are different. Because black hole pairs are usually equal mass. In the case of planets versus star, we are talking about 10 to the -3 or 10 to the -4 mass ratios.
Okay. So, I mean, will this your simulation results change if you have, multiple planets forming?
Yeah, there are going to be even more rings than gaps. Yeah, so each planet going to form their own gaps, and then you're going to see even more rings and gaps within the same circumstellar disk. Here, for simplicity, we only put in one planet per simulation, per disk, just to see its own effects.
Shubhendu, can I ask two more related questions?
Yeah, sure.
Okay. If we look at our solar system, then we know that there were, not all planets are formed, protoplanets formed, which had roughly circular orbits. Some of them had very eccentric orbits, right?
Yes.
If you put that in the simulation, how will the simulation change? I mean, or are you being able to create some planets with highly eccentric orbits?
Yeah, so there are two things here. So first of all, yes, if you have an eccentric planet, then it's going to also create a very eccentric gap. And the higher mass is the planet, the more likely it's going to be this eccentric gap. But there is another thing that, of course, as long as you're forming this planet in this gaseous disk, the gas is dumping the eccentricities and inclinations. So even if our planet starts off as eccentric and inclined, the orbit through this gas going to dump this eccentricity, and we're going to have a more circular orbit. However, once the gas dissipated, then from that point on, again, the eccentricities and inclination could again get larger, of course, through the dynamical interaction. But as long as there is gas around, that's going to dump all these eccentricities. Okay, and so it makes the planets more circular.
Will go away. You mean to say that the eccentricities will go away because of the interaction with the gas?
Yeah, during the gaseous phase, and then it grows again in the debris disk phase, right? When there is no more gas to damp it. So here, these simulations are representing always the gaseous phase, when the planets are very circular. Their inclination and eccentricity will grow once the gas completely gone away and we are in a debris disk phase, but these simulations are not for that. These are gas hydrodynamic simulations.
Okay. And the last question, since you are doing hydrodynamic simulations, at least in the early part of the simulations, do you see some jets forming?
No, there are no jets, but I think for jets, you would really need magnetohydrodynamics, so magnetic fields as well. And I do not have that in the simulations. However, there is only one such simulation for circumplanetary disk, and even then they found the jet only one single occasion throughout the entire simulation. So maybe they can form, but only transiently. This is so far the results, but there is no magnetohydrodynamic simulations, too many available in this field to really answer that question. This is for the future to study.
Okay, I'm done. I think I've taken a lot of time.
Yes, so there's a question from Priyanka Jalan. So she wrote that could there be magnetic field in young planets which can affect the accretion and lead to UV excess or any kind of emission?
Yes. So this is a very good question. So we know that magnetic fields of planets in the solar system today are much smaller than of the stars. Now, however, we know from stellar astrophysics that magnetic fields of young stars are much larger than of the adult stars or evolved stars that we see today. So maybe it's the same for planets. Maybe planets had larger magnetic fields when they were forming than they had today. And that would mean that indeed the magnetic fields might have an effect on the accretion, on whether a jet is forming, whether we can, ionize hydrogen more or whatever. Then the magnetic field might be also important. However, there are no studies available about what field strengths we could expect from forming planets. There is just no, because simulation-wise it's too difficult. Back of an envelope calculation is too simplistic to incorporate every effect. So actually we have no idea how strong the forming planet magnetic fields are. And therefore we cannot even estimate how much they would influence planet formation. So this is also something to study in the future.
There's another question from Arfan Ghosh. He wrote, how do you differentiate the H alpha and bracket gamma emission from CPD and CSD?
Yeah, so from the circumstellar disk, there was no, because we did not simulate the very close inner part of the circumstellar disk close to the star, which would ionize. I mean, we were really concentrating on the circumplanetary disk in this simulations. Observationally, whether you could distinguish between whether it comes from the circumstellar disk or the circumplanetary disk, I mean, if you can put the slit of the spectrograph onto the planet, which would be very far away from the inner circumstellar disk, then yes, maybe. But otherwise, if you have a wide field spectrograph, and you cannot localize the H alpha or Paschen beta, whatever, then you cannot distinguish, unfortunately.
Okay. So is there any other question? So Raj, please ask the question.
Okay, yeah. So when you showed that when matter interacts with the circumplanetary disk, so it creates a shock, right?
Yes.
So where does this shock settles? Because like it will heat up the surrounding material, then it will be transported outward. So do you using any kind of cooling processes there to?
Yeah. Yes, there is radiative dissipation inside the code. Yes. Yeah. So it's cooling.
Okay, so and is there any specific signature of that shock in the simulation other than this extra thermal gradient? So any rate this like other particle acceleration or any other emission processes?
I did not look into any other emission processes, but this is this shock is always forming, and it's stronger for higher mass planets because the accretion influx is scaling with the free fall velocity of the planet. So that means that higher mass planets going to have more supersonic velocities for this influx, and that would create a supercritical shock front. Versus for the smaller mass planets, the shock front is not supercritical. So therefore, I believe that all these processes would be different for high mass planets versus low mass planets, depending on how strong is the shock front.
Okay. Thank you.
Yeah, so another question is, how does the accretion shock from CPD affect the CSD?
How does the accretion from the circumplanetary disk affects the circumstellar disk? I mean, we see this meridional circulation that has been observed. I mean, we see that there is this, this constant reshuffling or mixing of the circumstellar disk material will also change the chemistry, because when the circumstellar disk material gets close to this hot planet, then everything heats up, the flow is heating up, and then it goes back into the circumstellar disk. So then this material going to be chemically altered, right? because of this temperature gradient that it goes through. So that's going to be different. I don't know what else we could say. I mean, just the fact that there is this meridional circulation means also that just the gap opening doesn't halt the accretion onto the inner circumstellar disk. So this is the reason why we see in a lot of ALMA images that there is also an inner circumstellar disk, and then there is a large cavity in the outer circumstellar disk. There is no problem with the cavity. It can flow through this meridional circulation, and the mass can flow through it. It wouldn't stop the material flux from the outer circumstellar disk to the inner circumstellar disk. So this is kind of all the effects that we can consider.
Okay, so I have a few simple questions to ask. So you said that it's very difficult to observe the Jupiter-Mass.
Tan Jupiter-Mass planet. Oh no, sorry, the Jupiter-Mass planets. Yeah, sorry. Yeah, the Tan Jupiter-Mass is easy. Yeah. Okay.
ALMA is the best one because mid-IR or near-IR is not so much visible, right?
Yes.
So do you think it will be helpful using JWST or ALMA or ELT?
Yeah.
So both of them.
One of my students is doing mock observations of that exactly. So yeah, I mean, the mid-infrared in GWST will be useful. But then again, you know, what sometimes observers misunderstand, they were like, oh, but we were always looking for planets in near-infrared. Now we did it wrongly. No, you did not do it wrongly. What I'm talking about, forming planets, embedded planets in the very beginning. Versus if you talk about evolved planets, the near-infrared is still great because there you get a large, the planets are really bright in near-infrared in comparison to the stars.
Yeah.
But if you talk about forming planets, then you have to go to mid-infrared or submillimeter or radio. Yeah, but yeah, so I believe mid-infrared would be the best. The near-infrared bands, no.
And another question is that, so the simulation always starts from Jupiter mass or Saturn mass, right? Not Earth mass. You don't start from Earth.
No, I started from zero. I build up the planet and then I just keep it fixed eventually. So it's not like I'm plunging in a Jupiter mass planet. I build it up with a so-called mass taper. Gradually, I build up the mass, say over 100 or 200 orbits of the planet. And then after 200 orbits, it remains the same mass, this Jupiter mass or whatever.
Okay, yeah. So there's another question is there from Kuntal Mishra. She asked, you mentioned that extinction is a problem. So in simulation, is the extinction accounted for? So do you take care of that?
Yeah, I mean, we solved the radiative transfer inside and the hydrodynamic simulation. So yeah, the extinction is taken into account, right? I mean, everything depends on the optical depth, on the opacity of the material, because that determines how much cooling, for example, we get locally, right? If it's very optically thick, it doesn't cool very, very much. This is why the circumplanetary disk is so hot, by the way, because it's very optically thick. And in the gap, we have low temperatures because the gap region is very optically thin, and therefore you have instantaneous cooling over there. So yeah, it's taken into account. I mean, we solved the whole radiative transfer equation inside.
Okay, and so when you think that you will have that ALMA observation and you can.
Yeah. So we already have the ALMA observations. It's just my student is starting with September to work on this because she's now having examination period. So we do have already the observations with us.
Okay. So are there any other questions? I don't see any hands there. So
okay. It's also time now.
Thanks, Judit.
1 o'clock.
Yeah, so, thanks, Judit, again. And we hope.
Thank you very much.
Yeah, we hope to have you here at Eris sometime in future when you can visit India then.
Yeah, I would love to visit. Yeah, hopefully we will be able to soon. Thank you. Bye-bye.
Yeah, with this we'll close for today and see all of you guys again next week. Take care and be safe. So, bye-bye. So you can also.
Yeah.
unset the screen and we'll talk to us.
Okay. Ciao then. Bye bye.
Bye bye.